Okay, so today we'll be discussing about waveguides. It's a continuation of what we were doing in the last class. So as usual, we'll discuss the basic concepts. We'll try to see some of the problems. Today I won't discuss many problems because the concepts, if you go through the concepts, that will suffice and you can solve the numericals. They are pretty simple if you can follow the concept. So I'll stress on the concepts here. And it's a continuation of what we were doing in the last class. So I'll first give a recap of what we discussed in the last class, and then we'll discuss mainly about the dielectric waveguides today. And finally, if you have any doubts, we can try to clear them. So as we had discussed previously, in transmission lines, there are two conductors that are involved, and their transmission lines can support TEM waves. What do you mean by TEM waves? It means that transverse electromagnetic mode, right? So there, if you have your propagation direction in a particular direction, like suppose the Z vector, then your electric field and the magnetic field of your electromagnetic wave will be perpendicular to the direction of propagation. Okay, so that's what TEM mode means. So E perpendicular to H, perpendicular to Z, considering Z is your propagation direction. So transmission lines support TEM mode. But what we saw is that waveguides, in general, if the waveguide consists of one conductor, where you can consider it to be a hollow conductor through which you are transmitting your signal, in that case, it does not support TEM modes. Okay, so it supports either TE or TM modes, transverse electric or transverse magnetic modes. And we tried to find how the electric fields look like in each of these cases, like the transverse electric and the transverse magnetic modes based on the boundary conditions, right? So this was the basic concepts where we had said that these two boundary conditions need to be satisfied at the inner walls of your waveguide. And so if you consider a general form of electric and magnetic field, if you apply the Maxwell's relations, okay, considering that electric field and magnetic field has components in X, Y, and Z directions, and if you put it in the Maxwell's relations, you get something like this, okay. And from here, you can write EX, EY, BX, BY in terms of EZ and BZ. Okay. So now, depending on whether your EX or EZ or BZ is 0, you will get some expression of EX, EY, BX, BY, which depends on this Z components of electric and magnetic fields. Okay. And from here, you can try to decouple by using this in the remaining two Maxwell's relations. You can try to decouple them, and if you do that, you get some equation like this, which is like a wave equation. Okay, so basically, you need to satisfy these two boundary conditions. And what you do is, if this is your wave equation, you can think of it as if this is the equation, how should your Ez or Bz look like, right? So in general, you can take it to be, suppose if you have TE waves, so transverse electric, that means there'll be no electric field component in the propagation direction. So that means Ez is 0. So now you can consider Bz to be a function of X and Y. You can write it as a product and try to use the concept of separation of variables. Okay, and this is what you do. Now here you apply the boundary conditions. Okay, so what you do is this gives you the boundary conditions. Here you are applying the condition that Bx should be 0 at x equal to 0 and x equal to a. And this is what you had done here, right? So Bx is dependent on del Bz del x. So derivative of Bz, right? So that's why if this is your Bz, you have to do a derivative and see that what is the condition where the derivative of x becomes 0 or 0 at x equal to 0 and x equal to a. And from here, you get the conditions for the wave vectors, wave numbers, right? Kx and ky. And that gives you the expression for Bz, right? And here, if you put this, like kx, ky, this is how they're related to the wave number. So from here, you can find an expression like this, which gives you the fact that below a certain cutoff frequency, waves get attenuated. Above that particular frequency, the waves propagate. So that is called the cutoff frequency, right? And we saw that for TE waves, the dominant mode or the lowest cutoff frequency comes at m equal to 1, n equal to 0. So TE10 is the lowest cutoff mode or lowest dominant mode, right? So from here, you can find an expression for the cutoff value at the lowest values of m and n, right? So this is what you get. So omega 10 is given as c pi by a, right? Frequencies less than this will not propagate. So that's how the waveguides behave as a high pass filter. And then what we saw is that you can write the wave number in terms of the cutoff frequencies, and it will take up a form like this. And we know that the wave number is related to the velocity. So from here, you can find the velocity. And as you can see, this is greater than c, right? So this wave velocity is the phase velocity, okay? And it can be greater than c, but if you find the group velocity, which is actually a component of like in that case, you actually have to take the component which is along this direction. And if you do that, what you find, or you can do it using this definition of the wave of the group velocity, and you will get something like this, which is less than the speed of light. So everything is consistent, okay? And you can also, so this is how you're writing it. So you can in general also write the wave number in terms of, kx, ky, kz as a vector, and consider it as a reflection that is happening at the surfaces, okay? And then as you can see here, the velocity down the waveguide is given as this component, okay, cos theta, which again depends on how your wave number is directed. So this was about how one can define the cutoff frequencies and the velocity of wave propagation through a waveguide, okay? And similar things can be done for a TM mode. What was interesting here was that in this case, when you apply the boundary condition, in this case, BZ is 0, EZ is not equal to 0, okay? And when you apply the boundary condition, which requires EZ to be 0, you have to put this expression. Like similarly, you have to do for Y as well. But when you put that, what you get is an expression like this. So this is how your EZ looks like for a TM mode, okay? And from here, you can see that the smallest or the lowest mode corresponds to the fact when n and m both equals to 1 and not 0, okay? So 1 is the smallest mode for the TM modes, okay? And from here, you can also find the cutoff frequency, which is similar to how you do for the TE modes. So these things were something which we had discussed previously. Now, based on that, if I ask you that how does the phase velocity look like inside a hollow metal waveguide? So which of the following should be correct? Is the phase velocity greater than the velocity of light in free space? Is it less than the velocity of light, or is it equal to it? Or is it equal to the group velocity? And if you remember, what we saw here is that if you see here, what do you get? You get that the wave velocity, which is actually the phase velocity, is greater than c, right? And this in a way also tells us how the wavelength inside inside a waveguide will differ from the free space free space wavelength, right? So this is important to remember that phase velocity of waves propagating in a hollow metal waveguide is greater than the velocity of light, okay? But if you look at the group velocity, that will be less than the speed of light, okay? Phase velocities are greater. And that tells us how the wavelengths differ inside the waveguide. Now, what we will concentrate today is this fact that there can be different kinds of waveguides. Okay, so when you talk about waveguides, you can talk about the optical fibers. Okay, and there you have to think of the spherical coordinate systems or the cylindrical coordinate system because of their structures. And that's difficult to analyze, so we won't go into that. but we'd rather look into planar waveguides, okay, which can be done based on rectangular coordinate system. So we'll focus on that, but similar things can be extended to optical fibers, which is a very important, which came as a very important application everywhere, right? Where optical fibers are used everywhere for optical transmission. But this kind of waveguides, the parallel, you can say, planar waveguides are also very useful when you talk about transmission on chips. Okay, so this waveguides can allow transmissions in terahertz regions, terahertz frequencies. So it's very useful. So today what we will discuss is this planar. First, we'll discuss about the planar mirror waveguides. So basically, what you have here is this two mirrors. You can consider it as mirrors because they'll reflect. Okay, and like we'll consider that the waves that pass through this region gets reflected at these two surfaces. Okay, suppose the incident angle is theta. So you have some wave which goes, hits here, and then gets reflected, and there are repeated reflections that is happening. So in order for the wave to propagate, propagate without any attenuation, we need to impose a self-consistency condition where we say that the wave reflects twice. When the wave reflects twice, so it reflects here and then it reflects here. So this point and this point, so the waves that are emanating here and the waves that we get here, they are same. So the waves reproduce itself after having two reflections at these two surfaces. Okay, and if that happens, then the wave remains unattenuated and it gets transmitted without any distortion. So the fields that satisfy this condition are called modes. Okay, so modes are fields that maintain the same transverse distribution and polarization at all location along the waveguide axis. So here, as you can see, for this condition to satisfy, what do we need? As the wave would propagate, see here, some of it would get, transmitted, some of it would get reflected. And now when the wave reaches here, for this to be exactly equal to what we started with, what do we need? We need that the phase difference that remains between these two, between the waves that has got separated, should be an integral multiple of 2 pi. Okay, so from here you can say that if the wave number is given as 2 pi by lambda, then 2k d sine theta should be equal to 2 pi m, where m is some integer. Okay, so this is your self-consistency condition that needs to be satisfied for the wave to propagate properly. Okay, now this tells you already that means there could be some particular values of theta m where this condition would get satisfied, right? And that is called the theta m value. So you can say that sine theta m is given as m lambda by 2d, okay, where m can be integers starting from 1. So now if you consider that there is some wave which is incident at some angle, okay, and it's propagating along z direction, so the wave number components could be given as kx, ky, kz, where kz is k cos theta, right? And ky, if you consider this transverse direction as y, then ky would be given as k sin theta. Okay, now if your medium inside in this material is having a refractive index n, then, and if k naught is your wave number in free space, then you can write ky as n k naught sin theta, right? So now you know that for the self-consistency condition, theta cannot be just any values. Okay, so it has to be some particular values, which comes from this relation. So if you put that relation here, you see that the wave vector here, kym, is a integral multiple of pi by d. So this tells us how the transverse component of the wave vector should look like. Okay, so this is for the case where you have some TEM waves propagating through these two surfaces. Here you're only considering the case that the self-consistency relation should be satisfied as they get reflected on, like as they have multiple reflections. Okay. And then if you look at the component along the propagation direction, that would give you the propagation constants, and that is given as beta. Okay. So if you use the relation that ky square plus kz square is equal to k, okay, then from here you can get to this expression for the propagation constants. Now, as you can see, suppose if you have these two layers, okay, and you can have different modes. So this, they can, like, the waveguide can support different kinds of modes. What this image is telling you, like pictorially, it is very easy to understand that the, suppose if your width of your waveguide is d, okay, then the maximum wavelength that your signal can satisfy, or the maximum, the mode with the maximum wavelength should be 2 into the width of the waveguide, right? So this is half of the wavelength. Another you can get here. So for the self consistency condition to get satisfied, from here you can say that if the given width of a waveguide is some d, then the mode with the largest wavelength should be given as 2 into d, right? Pictorially, that's how you can understand. So this is for a planar mirror waveguide, okay, where there is reflections from all these ends. And here what we consider is there'll be some pi phase difference whenever there is a reflection here and here. So at each reflection, there is a pi phase difference that would come up, okay? And so there'll be like 2 pi phase difference at this point. And what you say is the additional phase difference that comes up here should be an integral multiple of 2 pi for the self consistency condition to hold. Now, how can you find the number of modes here? So since we know that sine theta m is given as m lambda by 2d, so by number of modes, we want to find what is the maximum value of m, right? Now, you know that sine theta m should be always less than equal to 1, right? And that limits your value of m. So from here, you can find the number of modes that your planar mirror waveguide satisfies, or the maximum number of modes that it can hold, okay? And from here, you can also find the cutoff wavelength. So this is now mathematically, you can see that the wavelength lambda c equal to 2d is the cutoff wavelength of the waveguide. Okay, so it's the longest wavelength that can be guided through the structure. So pictorially, we got the same understanding from here, and this is how you get it mathematically. And you can change it to the cutoff frequency just by using the, so if you know the velocity of your wave, so you can find the cutoff frequency or the angular frequency. Okay, and you can use that relation in the expression for the propagation constant. So if you look at this expression here, you know pi by d, right? And this pi by d also comes up here. So from here, if you use that relation, you can write how your propagation constant, that is the component of the wave vector in the direction of propagation. That is what is the propagation constant. And you can write it how it depends on the frequencies. Okay, this is your cutoff frequency. This is your frequency of operation. So this is how your dispersion relation will look like for a planar mirror waveguide. Now, if you come to a planar dielectric waveguide, where now what you have is, this is some layer with some dielectric constant, and you have a layer above, you have a layer below. Okay, and they can have, they will have different dielectric constants. Now, the lower and the top layer can have different dielectric constants, or can also have same dielectric constants. Okay, so a planar dielectric waveguide is a slab of dielectric material which is surrounded by media of lower refractive index. It's important. Why? Because if it is of lower refractive index, then you will get the condition that's required for total internal reflection. Because reflection is very important. You don't want your light to get lost in transmission, right? You want your light to be, or your electromagnetic wave or your signal to remain confined in this region, so that it gets propagated and you get the signal. Okay. So for that condition, you need lesser transmission, you need more reflection. And for the condition of total internal reflections, it's required that the wave goes from a denser medium to a optically rarer medium, right? So N2 should be less than N1. So that's what is written here. Now the light is guided inside this slab by total internal reflection, and in thin film devices, this is called the film, okay? And the upper and the lower media are called the cover and the substrate. So this is your cover and this is your substrate. The inner media and the outer media can also be called core and cladding, and this is mostly used in the terminology for optical fibers, where we say that the refractive index of the cladding should always be less than the refractive index of your core. Okay. Now in this section, what we see is, now we want to see how, while the light is getting propagated in this dielectric waveguide, okay, how do they propagate? Okay, so what are the different modes that they support? Okay, what are the frequencies? What is the cutoff frequency? That's what we want to find. Now here you see that suppose the light makes some angle theta. Okay, so it's making some angle theta with the direction of propagation of your wave, right? And then for it to have total internal reflection, we know when total internal reflection happens, right? When the angle of incidence is greater than some critical angle. So that's what is being written here. So it says that if your incidence is at an angle greater than the critical angle, then it would suffer total internal reflection, and so the waves would remain confined in the film. Okay. And if they are larger, so here it's a complement just because you have, so see, this is the critical angle, and this is complement of theta because it's inside this right angle triangle. That's why it's said that if you are just looking at how the rays are getting incident, in that case you have to say that rays making angle larger would refract, okay, and if they are smaller than that value, than the critical value, then they will get reflected. Okay, so this is how the complement of the critical angle is related to the dielectric constants of the different mediums of the core and the cladding. Okay, now let us look at the waveguide modes. So if you look at the waveguide modes, consider that you have some TEM plane wave, okay, and you know how what the refractive index is, so you know what is the wavelength of your light or of your wave inside that medium. And now you say that it's getting propagated, so there'll be some phase that it will acquire as it propagates, right? Now if you have to again consider the self consistency condition that we had discussed, then the wave here and the wave here should be same. And for that to happen, what should be the case? The phase difference between this wave and this wave, that is the reflected and the transmitted wave, should follow certain conditions. And that is what is being given here. So AC minus AB, this phase difference is equal to 2D sine theta, where D is your width of your film. Okay. And that should be, now this is important, I'll come to that. That plus the phase that it has acquired while it has got reflected. Whenever there is a reflection, it can acquire some phase, right? If that phase is given as phi r, it has gone through two reflections, right? So 2 into phi r, and this total, this phase that it has acquired should be an integral multiple of 2 pi. Only then the self consistency condition would satisfy. And from here you get a relation which gives you a relation of the transverse wave components. Okay, so the transverse wave component should satisfy this relation, right? Now here it's interesting. Initially, when we were talking about planar mirror waveguides, we considered phi r to be a pi phase shift, right? But when you have a dielectric, you would have some phase shift which is given as phi here, and that would be a function of your angle theta. And how to think about it? Think about it in terms of the Fresnel coefficients, right? So when you have some reflection from one medium to another, we know that as it goes through that medium, a part of the wave would get reflected, part of it will get transmitted, and that comes from the reflection coefficients. And your reflection coefficients in general can be complex, right? So the wave can attain some phase, extra phase, as it gets reflected or transmitted. And this phase is again a function of how the waves get incident on the interface. So in case of a mirror, it's always a pi phase shift, which comes from the Stokes treatment. You can consider, and you can see that while the transmitted light has no extra phase acquired, the reflected light has a pi phase shift. But for a wave guide, which is like a dielectric waveguide, this would be a function of your incident angle, right? So now, before we look at how this phi comes up, let us just look at the reflection and refraction that happens at an interface, just for us to recapitulate. So what you see here is that you have some incident wave, it gets reflected and part of it gets refracted, right? And we know that this is how the Fresnel coefficients look like. These are the Fresnel equations, okay? Now here, you can also apply the Snell's law, which relates the different angles that are involved, right? So theta 1 and theta 2 are related by the Snell's law, and that's what is being given here. Now, in general, as you can see here, this has some square root involved, right? So depending on how n1 and n2 are, or how the incident angle is, your quantities can be negative. These quantities can be negative. So this can be it can have some imaginary parts as well. Okay. So in that case, your reflection coefficient and as well as your transmission coefficients would acquire some phase. It would be a complex quantity, right? So that's what is being given here. So in general, you will have some magnitude of Rx, you'll have some phase shift because of Rx, and similarly for Ry. Now let us look at the case for TE polarized light. Okay, so transverse electric waves. And in this case, there can be two cases. Now, depending on how your N1 and N2 are, different cases can arise, right? So if your N1 is less than N2, here what happens is if you put these values here and try to simplify, you would see that the reflection coefficient is always real, okay, and negative. And that corresponds to a phase shift of pi because it's negative. So that corresponds to a phase shift of pi, okay. And this is the magnitude in case where you put theta 1 equal to 0, that is normal incidence. All this is coming from the Fresnel equations, which we had initially discussed. So it comes from satisfying the boundary conditions at the interface, okay, when you have two different media. But now we are trying to do it for different polarized light, and we are trying to include the cases of what happens when N1 is greater than 0, greater than N2, or vice versa. So when N1 is less than N2, you see that your reflection coefficient is always real, okay? And if you plot the reflection coefficient, it would look something like this. So it would increase and reach 1 at some values where the argument is always pi. So that shows a pi phase shift, right? But when you have internal reflection, this is what happens when you have your waveguide. Okay, in waveguides, we always talk about the case where your cladding has a lower refractive index than your core. So there, what's interesting is this internal reflection. And here what happens is, for smaller angles, the reflection coefficient is real and positive. And this is the value, like putting theta 1 equal to 0, you get a simplified expression. Okay, but then it increases gradually to a value of unity. And this unity is attained at some critical angle, right? And this is your critical angle. This comes from here, right? This from this condition. So this is called your critical angle. So if you plot it here, you would see that at some critical angle, your reflection coefficient becomes 1. That means here there is no transmitted light. Everything gets reflected. Okay. And you can also plot your argument, and the argument would look like this, right? So now, if this is your argument, you can try to express it in terms of your incident and reflected and refracted angles, and this is what you get. Okay. So what we'll do now is, this is telling you that the phase that the wave acquires is a function of your incident angle. Okay. Now we'll try to implement this in our discussion for the waveguides. Okay. So here we saw that for the waveguides, this is the condition that needs to be satisfied for the self-consistency condition. Okay. Now, And this is just writing it in terms of the wave number. Now this phi r satisfies this condition. Okay, and this is coming by putting this conditions in this expression here. This is the general expression that comes from Fresnel equations. Okay, so if you do that, now you see that your phase acquired is a function of your incident angle. Okay, and if you put that expression here, okay, you would get something like this. So here, when you are writing phi r, you are now writing phi r in terms of you're using this relation to replace phi r. Okay, and then this is what you get. So this is your self consistency condition for TE modes. Now similarly, you can try to see how these expressions change for TM modes, right? Then you have to use this relations, and accordingly you have to solve. So there, this expression will be slightly different, but then that would give you how the phase changes as a function of incidence angle for the TM modes. Okay, and that would come up here. So this is the self consistency condition for TE modes. And what is this? So this is a transcendental equation. So here you have to plot this, you have to plot this separately and see where they intersect. That gives you your solutions. Okay, and as you can see here, if you plot it for some values, you would get something like this. So as you can see, they intersect at some particular points until they reach this point. Okay, where they have reached the, so this is the critical point. Okay, because there can be no values beyond this point. Okay, so this limits your value of theta m. Okay, so as you can see here, for this particular case, the intersection points, this points, like if you look at this points, these are the corresponding points for your planar like mirror waveguides. Okay, the open circles correspond to these values, which provide the bounce angles for planar mirror waveguide of the same dimensions. But for a dielectric waveguide, your solutions are given by this intersection points. Okay, and as you can see, if in this case where sine theta c complement, so this is your critical angle, is some 8 times of lambda by 2d, and there you see that you get 9 intersection points, right? So then the number of modes that your waveguide satisfies or waveguide supports is actually 9, right? So that means depending on what your critical angle is and the dimensions of your waveguide, you can find out the number of modes that your waveguide satisfies. Okay. So now again, we use the relation that sine theta should be less than equal to sine theta c. So that limits your like your angles theta can extend only up to the critical angle complement. So if you do that, that limits your value of like the number of modes that your waveguide can support, right? So this gives you the number of modes. Okay. Now in general, you can also write it as 2d by lambda naught into NA, where NA is given as, this is the numerical aperture, which is dependent on how the refractive index of your core and claddings differ. Okay, so this NA is the sign of the angle of acceptance of the rays. So depending on this numerical aperture, like physically or by physical interpretation of this would be that the numerical aperture gives us a measure of how, like till how much can your light get collected by the optical fiber. So the angle of acceptance of rays, how from how far of an angle can the rays be taken up by the uh, uh, optical fiber or the waveguide. Okay, so this is your numerical aperture, and this is how the numerical aperture is related to the dimensions, and this is how we can get the number of TE modes. Okay, now when lambda by 2d, okay, lambda is your, remember that lambda naught is your wavelength in free space and lambda is your wavelength in the waveguide. Okay, so it is n into lambda naught, where n is your refractive index of the media. So when lambda by 2d, that is this single, so suppose if this is your lambda by 2d, right? So when lambda by 2d is greater than sine theta c, what would happen? See, here, suppose this is sine theta c, right? If your sine theta c was somewhere here, right, and lambda by 2d was somewhere here, that means you would, in that case, get only one single waveguide mode, single mode. So this, when this condition is satisfied, and this can also be written by this relation, right? So putting m equal to 1. So in that case, 2d by lambda naught into Na is less than 1. There only one mode is satisfied. So if there are questions which say that if you have a single mode waveguide, if you know if you suppose know the dimensions of your waveguide, you know the wavelength that is propagating, then what should be the refractive index of the core or the clad given the other value? In in that case, what you have to use is you have to use this relation, right? So this is the relation that is there for a single mode waveguide. Okay. And in dielectric waveguide, there is at least one TE mode. Okay. And that corresponds to the case where m is equal to 0. Okay. And each of the other modes would have their own cutoffs, which is trivial. Now, in terms of frequencies, you can always change from wavelength to frequency, right? If you know the velocity, and that is what is being done here. So this equations in like it pretty much sums up how you can use or how you can find the number of modes, or how you can find the cutoff frequencies. All of this comes from the same relations. So I could see questions which says that, you're like, by using this relation, there were some questions in the assignment where you just have to use this relation in order to find maybe the refractive index. In some cases, the refractive index n1 and n2 might be given. You might have to find the numerical aperture. In other cases, suppose your numerical aperture is given, okay, and the relative ratio is given. So in that case, what you can write is you can try to find n1 from the numerical aperture and the relative ratio, and then you can also try to find n2. So that by that you can find what should be your value of refractive index for core and clad. Okay, so these are pretty much the concepts or the theorems or formulas that is required for understanding how propagation happens inside the wave. Okay, uh, I think that's it. Do you have any question? Are there any questions on any of what we discussed? I think most of the assignment questions were pretty straightforward, which were based on these concepts. Okay, so I guess there are no questions. So in that case, thank you. So in the next class, I think it's about antennas, and that's what we'll have in the have tomorrow. I was traveling, so that's why I could not take the class last week. So see you tomorrow then. Yes, yes. Tell me. Yes, please go ahead. I thought you raised your hand. Okay. Okay, so I guess maybe that was by mistake or something. Um, okay. So then see you tomorrow. Bye. Okay.